All right. So the plan is I'm going to have those graded by next class period. I'll pass those back tomorrow. We'll go ahead and talk about any questions you might have. And then we should be on track to finish up this lesson over polar coordinates by Thursday. Because my plan is we come in on Friday, we have nothing to do but SEL, we relax, we just wait for our vacation to start. Okay. The only other thing on Thursday, they're going to be calling you down to the auditorium by your classification, like freshman, sophomore, etc., at different times for Play It Safe training. So they're going to be showing you some videos, I guess. I don't know. Well, if I get some more information about that, I'll let you know. But the rest of this week should be pretty standard. Are there any questions? Hello, Caroline. Okay, so let's see what we got here. So yesterday we started talking about polar coordinates. Yes. Yes, Steve, you're back. Okay. Okay, so we started talking about polar coordinates, and we introduced some new vocabulary. Okay, so we're accustomed to using the rectangular coordinate system. Now, where the two axes intersect, we call it the origin. But in a polar coordinate grid, we don't call it the origin anymore. We call it the pole. Okay, so we now have the pole and what we used to call the positive x-axis standard position. We now refer to that as the polar axis. Okay, so we got a little bit of new vocabulary coming into this. All right, now this is what your polar coordinates are going to look like. The first value is the radius, while the second value is your angle theta. So as we were looking at yesterday, you want to go ahead and identify the angle theta first. So start with the second value, and then from the pole, go towards the direction of your angle, whatever the length of your radius is. Now, as we went through, we started to see different types of points. Okay, what happens if your radius is negative? There you go. You don't go towards the angle, you go in the exact opposite direction. Okay, everybody seemed to be responding to those pretty well. And then with this example here, we got the idea that there's an infinite number of ways to go ahead and write the same location as a polar coordinate. Okay. And then what we started to do after that was practice writing additional points that are equivalent to the location of one given point. Okay, so what we do is we rotate a full circle in the opposite direction. Radius is staying the same. Rotate a half circle in either direction, and the radius is going to be opposite. So we're always going to be looking for 3 additional points, 4 total. 2 where the radius is positive, and 2 where the radius is going to be negative. So if you start out with a positive angle, like here we got 3, 5 pi over 6, what it means when it says rotate a full circle in the opposite direction is you want to add or subtract 2 pi. So because it's a positive angle, we would subtract 2 pi there. Okay, that's going to keep the radius the same sign as what you started with. Now, if it happened to be a negative angle, well, then we would add 2 pi. Again, that's going to keep the radius the same sign. If I wanted 2 additional points where the radius changes sign, whether from positive to negative or vice versa, well, then I'm going to take my angle and I'm going to both add and subtract pi. That's the half rotation that we were talking about there. Okay. And we went through several examples, and again, everybody seemed to be doing pretty well. Well, what I want to go ahead and do now is actually start comparing polar coordinates to rectangular so that we can convert from one to the other. So the image on the far right above allows us to see the connections between polar and rectangular coordinates. Using this, we can quickly find relationships that allow us to convert between the two. And you'll notice it forms a right triangle, just like we've been looking at this entire time. Okay, so here we go. Converting from polar to rectangular. Now, we already know from trigonometry that the cosine of theta is equal to x over r. And we know that sine of theta is equal to y over r. Well, you remember way back in the day when we went ahead and solved for both x and y, we multiplied through by the radius r. Okay? Well, that's exactly what we did here. So if we're going to convert from polar to rectangular, x is equal to the radius times cosine of theta, and y is equal to the radius times sine of theta. Very, very simple identities. So let's go ahead and give it a try. Let's take the polar coordinate 2 comma pi, and let's rewrite it as a rectangular coordinate. Now, one thing about these, you always want to make sure that you're ending up in the same quadrant or the same location. So for this one right here, let's say we start rotating from 0 radians, we get over to pi. We have a radius of 2, so let's say this is 1 unit, 2 units. So let's say that polar coordinate would be right there. Okay, now because it's on the axis, we know that's a what? What's that big word starts with a Q? Quadrantal, exactly. So, I mean, just looking at this right here, you could probably go ahead and tell me what the equivalent rectangular coordinate's going to be. Anybody got a guess? Yeah, negative 2, 0. All I did was move 2 units left of the origin. But let's go ahead and see how that works out. I've got my radius, I've got my angle theta, so let's plug it in. So x equals the radius 2 times the cosine of pi, and then y is equal to the radius 2 times the sine of pi. I'm just using those two identities that we were provided above. Going from polar to rectangular, that's usually pretty easy, pretty straightforward. Now, tomorrow, when we start looking from rectangular to polar, that can get a little tricky sometimes because of our inverse, but I'm getting ahead of myself. Can anybody remind me, what is cosine of pi? Negative 1. Yeah. Remember, when thinking about the unit circle, we're thinking about these coordinates here at pi radians. You have the coordinate negative 1, 0. Remember, that's not going to match up here. We're doing polar and rectangular. Okay, so don't worry about that. So remember, cosine represents the x value. Yeah. So cosine of pi would have to be negative 1. So this is 2 times negative 1. And so I know my x value is negative 2. So likewise, what's the sine of pi? Okay, sine of pi. What's the y value at that location? 0. So the sine of pi is 0. 2 times 0 is 0. So there's my x, there's my y. So the polar coordinate 2 comma pi should be the rectangular coordinate, negative 2, 0. Oh yeah, give your best. That's all there is to it. Okay. Any questions? Easy? Okay. Okay, cool. Let's try another one. 4 and then 5 pi over 3. Okay, so let's start off real quick. What quadrant would this polar coordinate be in? It would be 1, 2, 3, or 4. It'd be in 4. Okay, we got a positive radius with 5/3 pi. Okay, so I'm going to go ahead and set this up. So radius and theta, x is equal to the radius 4 times the cosine of 5 pi over 3. And then y is equal to the radius 4 times the sine of 5 pi over 3. So let's go ahead and diagram this triangle. So let's say I rotate all the way around here. So that would be 5/3 pi. Can anybody tell me what my reference angle would be? Pi over 3. There we go. Now remember, we're going to do this on the unit circle. Pi over 3 is equivalent to 60 degrees. So does anybody remember what that fraction was across from 60? About 1/2. Square root of 3 over 2. And because we're in quadrant 4, we're going to go ahead and make that negative. Now across from 30, that'll be 1/2. So see, now I can determine the cosine and sine of that particular angle. Cosine of 5 pi over 3, that would be 1/2. And 4 times 1/2, well, that would be 2. And then the radius 4 times the sine of 5 pi over 3 would be a negative root 3 over 2. So somebody help me out. What would a 4 times a negative root 3 over 2 give me? And we're talking to today. Thank you, sir. Thank you. Negative 2 root 3. Okay, so I've got my x, I've got my y. So 4 5/3 pi should be in the exact same location as the rectangular coordinate. 2 negative 2 square root of 3. And you'll notice we have a positive x and a negative y, so that is definitely going to be in quadrant 4. So let's match it up. Okay. Anybody having a hard time with this? All right. Oh, I know what you're thinking. Let's go ahead and try one on your own. Try C. Okay. I'll give you about a minute. Now, very quickly, before I start the timer, we got the point -3, 7 pi over 6. What quadrant would that be in? Okay. Sarvesh? 3. See, it almost makes sense because 7, 6 pi is in quadrant 3. Why is it in 1? Remember, when you have a negative radius, you go in the opposite direction from your angle. So it would be in quadrant 1. Good. Okay. So let's see if we can come up with that rectangular coordinate. Yes, let's see. We got it here at 55, right? Fourth period. If it gets back in like the next minute, I can let you go, but they're about to lock the restrooms. So we'll kind of see how that goes. Okay. Normally, I'd like to go ahead and get some folks to, tell me what you got. But since we're getting short on time, let me go ahead and just write down the answer here. I believe I want to make sure I stay. Okay. So here's what you should be getting. 3 root 3 over 2, and then 3/2. That's a 2 right there. There we go. 3 root 3 over 2, and then 3/2. Okay. How many people were able to get that? Okay, good, good, good. So let's walk through it. So I'm drawing a triangle in quadrant 3. Okay, there's 7 pi over 6. Pi over 6 is 30 degrees. Ooh, I don't know, Lexi. I mean, you could try. Sure. Okay. Let's see here. We just saw this triangle a moment ago. Across from 30 was 1/2. Across from 60 is the square root of 3 over 2. Remember, we're in quadrant 3, so they're both negative. Okay, so this is going to be -3 times, well, the cosine of 7 pi over 6 would be a negative root 3 over 2. So when I multiply those, I do get that product right there. And then -3 times sine of 7 pi over 6, that would be a -3 times the -1/2. And that's where I would get that one. And you'll notice both x and y turned out to be positive, so it's also in quadrant what? Quadrant 1, so we're good. Okay, so that is how you convert a polar to a rectangular coordinate. How we doing? Okay, well, we got less than 5 minutes left. I need you to go ahead and get those calculators back up to the front for me, please, so I can get you out of here.